Thank you. And now, is it the last slide or we going to another slide? This is the last slide, right? Last time we were on there? Yes, very good. Thank you. Now, all right. So, so everybody's okay. When the cell number is 1, which is closest to the nucleus, cell number 2 is the next, cell number 3 is the next, and cell number 4 the outermost. So these are energy layer, right? Closest to the nucleus, the next, the next to the next. And when a cell number 1, it has one cell subcell orbital is 1s, and it has 2 electrons, maximum number of electron 2. When cell number 2, it is a 2s and 2p. 2s, right? 2s and 2p. That's what we said earlier, right? 2s and 2p. Now 2p could be distributed into 3. 2px and 2py. Remember? So 2px, 2px, 2py, and 2pz. Right? That's basically 2p. Let me write down here 2pz. So we are basically reviewing it, right? 2pz. And each and every one can hold 2 electrons. 2, 2, 2. So it's a rule of 2. And why do they do that? Because of the spin pairing. Because of the spin pairing. We're coming next. So on cell number 3, you have a 3s, 3p, 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 meaning px, py, pz. 5d orbitals. So 5d orbitals meaning dx square minus y square, dy square minus dz square, dxy, yz, and zx. Each and every one can have 2 electrons. The 2 times 5 is 10, and 3 times 2 is 6, so 18. And you can go on like that, the same way. 7f, f orbital can hold 7. It is a 7 coordinate, so 7 times 2, 14 electrons. So you have gone through this one, right? So what you saw, each and every orbital can have only 2, not more than 2. Maximum number of electron 2. And why is that? Because of spin pairing. Because remember, electrons cannot stay together because of the negative charges, right? Negative charges repel, positive charges repel, negative positive attract. But since you have 2 electrons in each cell, subcells, or orbital, whatever it is, that means they can stay together. And how do they stay together? Because of the spin pairing. Because of spin pairing. So what is the spin pairing? The spin pairing is an electron is moving in the anti-clockwise directions. There's a counterclockwise, moving in the anti-clockwise, right? Counterclockwise, creating a north pole and south pole, a tiny magnet, because of spinning. So electric field is converted to magnetic field. Likewise, if you have another electron spinning in a clockwise direction, so counterclockwise, clockwise, and therefore this is creating south pole and north pole. Now, as you probably know, north pole and south pole attract, right? North pole and south pole attract, south pole, north pole attract. That means they can stay together. So by spinning, the 2 electrons can stay together by spin pairing. That's called spin pairing. Spin pair. Because creating 2 tiny magnets, north pole and south pole, and south pole and north pole, now they can stay together. So that's the meaning of the spin pairing. So once again, we have rule of 2. Any subcell, cell, subcell orbitals, whatever it is, maximum number of electrons they can hold 2 electrons due to the spin pairing. Spin pairing. Everybody okay with it, right? All right. Then let's go to the electronic configuration of the atoms. That will provide the electron distribution of an atom in the extranuclear space. Number of electrons at the outer shell, also known as valence shell, and position in a particular periodic table. These things you can get it from the electronic configuration. We can also get another things called Lewis dot structure, and I'll show you in a minute. So these are the information we can get from the electronic configuration. And as we saw that so if we take a cross section, for example, if we have a, let's say, electron, for example, like this. So this is the electron distribution. And if you take a cross section like this, just take a cross section like this way. If you take a cross section, it will look like this. It will look like this. So nucleus is right here. That's our nucleus right here. Those are protons or neutrons are sitting right here. And the next first one is the principal quantum number or cell number 1, and it has the 1s, and the maximum number of electrons S can hold is 2 because of the spin pairing, right? Because of spin pairing.
Professor Datta,
Yeah.
can you go back to the last slide really quickly?
Sure. So this is the things that we can get from the electronic configuration of an atom: electron distribution at the extranuclear space, number of electrons in the outer shell, which is also known as valence shell, and we can also tell by looking at the number of electrons in the outer shell which group of the periodic table that elements belongs to. That also gives some periodicity. Periodicity is the properties of elements in a particular group. So elements in a particular group will show similar kind of properties, and that is known as periodicity. The periodicity. Shall I move on? All right. Okay. So once again, if you take the cross section of those extranuclear spaces, the subcell, cell, subcell, and orbitals, then we can get like this. Cell number 1, that is 1s. Cell number 2 has 2s and 2p. 2p is further quantized or further split into 3, right? px, py, and pz. We already saw that, right? px, any p can be split into 3-dimensional. px, py, and pz. That's basically the p orbital or the p subcell. All right. So when cell number 3, third cell, a little bit away from the nucleus, you have a 3s, 3p, and 3d. 3s doesn't split, 3p will split again, 3 of them, 3px, 3py, and 3pz. Now, the 3d can also split 5 different coordinates. You have a 5 different coordinates, and I already give you, right? 3d x square minus y square, 3d y square minus z square, 3d xy, 3d yz, and 3d zx. Those are all 5 different coordinates. Now, based on the energy calculations, from the quantum mechanical calculations, the energy of 4s on cell number 4 is the energy of 4s subcell or cell is lower than the 3d. So that's why when the electrons will be filling up, the 4s will be filled up first, then the 3d. So this is the exception, remember, right? So on cell number 4, likewise, 4s will be filled up next after 3d. Then 5s comes up before 3d, 4d. Likewise, 5d comes up before 4f. So these are the little bit anomalies, little bit not following properly, and that is because of the electron, the energy levels. So most of the things that we'll study here will basically stop almost 3d and maybe 4s and 4p if necessary. We're not going to go further details of the elements that we'll talk about the electronic configurations. So we do not have to go too much complexity on here, but hopefully we'll stop around here. The 3D, so 4s comes before the 3D. All right, that's the 3D will cover about elements number 30. That's a zinc elements, and that's good enough for the time being. So once again, the order of filling is the 1s, then 2s and 2p, 3s and 3p, 4s and 3d. All right. These are the rules. There are 3 rules. Rule number 1. In the electronic configuration of an atom, the first orbital closest to the nucleus will fill first. Meaning, this is the nucleus. Remember, nucleus has a positive charge, and these are electrons are negative charge. So the closest one is a 1s. This will be filled up first. Then 2s will be filled up, then 2p will be filled up, and it goes like this way. So it's going from lower energy to higher energy. That is called rule number 1. So once again, there are 3 rules that dictates the electronic distribution of the atom at extranuclear space. The first rule is electrons will go to the lowest energy shell first, shell, subcell, or orbitals. It will go to the lowest energy, that is 1s. Once this one is filled up, it will go to the next energy level, that is 2s. Then we'll go to the next 2p, and 3s, 3p, 4s, and 3d. It will go like this way. Rule number 2. So everybody okay with rule number 1, right? That's rule number 1. electrons will fill up from lower energy to the higher energy. 1s, 2s, 2p, 3s, and so on and so forth. Rule number 2, each cell subcell will have maximum number of electrons, 2 electrons. So rule number 2, each cell subcell or orbitals can have maximum number of electrons is 2, only 2. Why? Because of spin pairing. So that's rule number 2. Any subcell, subcellular orbital can have 2 maximum number of electrons due to spin pairing. All right. So that's the second rule. Third rule is as follows: when let's say when 2s is filled up, for example, 2s2 is filled up, then you have a 3 electrons, for example. Let's say you have a 3 electrons still there. So you have a 2 plus 2, 4 plus 3, 7 electrons now. 2 of them are in the 1s, 2 of them are 2s. You have a 3 more electrons remaining, 3 electrons. So where will they go? They'll go to 3p, a 2p. 2p has 3 same energy layers, px, py, and pz. So what will you do? What they do is follows: these electrons, 3 electrons will go one at a time. It will go 1 to px, 1 to py, and 1 to pz. So once again, it will go 1 to px, 1 to py, and 1 to pz. So they'll distribute it in 1, 1, 1. It will not go like this way: the 2px2, 2py1, 2pz0, or vice versa. It will not go like this. It will go 1, 1, 1. So what it says, that if you have a subcell which has a similar or identical energy layers like a px, pi, pz, then electrons will be distributed one at a time, one orbital at a time. One will go to the px, next will go to py, next will go to the pz. One at a time, they will not fill up. This is called half filled. Why half filled? Because remember, each orbital can have 2 electrons spin paired, but you have only 3. So 1, 1, 1. These 3 electrons are unpaired electrons. And this is known as Hund's rule. Once again, what is the Hund's rule again? So H-U-N-D, Hund's, S apostrophe S, right? Hund's rule. And it is like this way. It's a Hund's rule. So Hund's rule says, once again, the Hund's rule says when the atom has more than 1 equal energy layers, equal energy orbitals, like a p, px, pi, pz, electrons will be distributed one at a time. All of them will be filled up first. This is called half filled. Then, if you have additional electrons, they'll come to fill it up. So if you have 4 additional electrons, like oxygen, like 8, then it will make the spin pair to px, then py to pz, and will go like this way. That's a third rule. So Hund's rule, everybody okay with the Hund's rule, right? All right. So this is the rule number 1, 2, and 3. I already showed you. Do not have to write it. If you already wrote it, then they're all there. Orbitals fill in the order of increasing energy: 1s, 2s, 2p, 3s, and 3p. That we will saw. Each orbital can have 2 electrons spin paired. That we also saw, right? Then, if you have electrons, when there is a set of orbitals with equal energy, px, pi, pz, one orbital becomes a half filled before any of them become completely filled. In other words, px1, py1, pz1 before they become px2, py2, and pz2. So that's the third rule. All right. Now, how to represent the electronic configuration in a piece of paper? We can do 2 different ways. More preferable the second one. The first one, so this is called representation of electronic configuration of an atom. You can use the box diagram. Not very popular, but many people use it for the sake of simplicity. Or you can use the cell number with the subcells and orbitals containing appropriate number of electrons. This is the one you will see it here. All right. But I'll give you some example how the box diagram works. So representation of the electronic configuration usually is a box diagram, or you can just tell number. I think someone is still chatting. Can you please stop the chatting, please? When you are talking it? Yes? All right. All right, otherwise I'll turn it off if you do not do that, okay? All right, so box diagram is as follows. So box diagram looks like that. A box represents an orbital, an arrow represents an electron. So that's basically like this. So that's basically our the orbital. And electrons represent two electrons, right? That's a spin pair. One is clockwise, one is counterclockwise. Like this is 1s2, 2s2. So that's a carbon. Carbon has 6 electrons, atomic number. So the 1s2, 2s2, and then you have 4 electrons. You have 2 additional electrons that go to px1, 2px, 2py1, and 2pz0. So that's called expanded electron configuration. 1s2, 2s2, 2px1, and 2py1, 2pz0. You don't have to write it. You can also write condensed electronic configuration, 1s2, 2s2, and 2p2. These 2p2, yes?
If we have this on a test, do you want us to write the expanded or condensed version? Like, can we just write 2p?
Both. Because you see, it's a both. You can say why I'm telling it. The expanded condensed one doesn't give you how many electrons are distributed in orbitals, whereas expanded one will give you the information. And why do you need the information? I'll give you the example very soon, within a few seconds, right? All right. So you have to know both. You have to know both. Very good. Now someone is still chatting. Would you please stop that, please? I would appreciate it. Okay. Otherwise, I have to turn it off. Okay. I don't want to be rude. All right. So let's see. Yes.
Oh, so where are you getting like the X's and the Y's from?
So the px the p orbital, p subcell is split into 3 different coordinates, 3 different axes, px, py, and pz. Let me show you I'm going to leave it like this way. Let me go a little bit further. So orbitals have a definite shape and orientation in space. 1s looks like one tiny ball close to the nucleus. Nucleus is inside. 2s is a bigger ball, only one. It can hold 2 electrons. Then that's a p. That's your 2p or 3p or 4p. Any kind of p orbital, p subcell, is split into like this. It could have a px x-axis, it could have a py axis, and pz axis. So when the electrons will come, it will go like this way. First one px, then another one will go to py, then another will go to pz. Then if you have additional electrons, it will fill up the 2px, then the 2py spin pairing, and then finally it will fill up the 2pz. So it goes like this way. So these are the 3 different coordinates. If you have the d orbital, d subcell, that is 5 different like this. Of course, we are not drawing it, right? It will be too clumsy, cannot be able to see it. So d subcell has a 5 d orbitals, very similar to like this. F subcell has 7 orbitals, 7 equal energy levels, 7 orbitals. So that's why 7 times 2, it can hold 14 electrons. That's so 7 dimensional. Of course, we cannot write it here. It will be too clumsy, right? If you have a G subcells, right? S, P, D, F, and G. G is for George, G. Then that has a 9 coordinates or 9 dimensional. And each dimensional contains 2 electrons. Therefore, 9 times 2, 18 electrons. Obviously, they are very, very complex. So P is the simplest version because you always know X, Y, Z, right? X coded 3 dimensional. So Px, Py, Pz, that's basically the orientations. All right, let's go back to our spin the orbital box diagram. That's orbital. Yeah.
I had another question regarding that. So do you want us to write the like subscript of X, Y, and Z whenever we write out the expanded form, or can we just write like the 3 different ones, just all 2p?
No, you have to write the expanded one. You have to write the expanded one. As I told you earlier, my questions are usually multiple choice questions. Therefore, you will have it will be asked in a way that you must know both. You must know the both in the expanded as well as the condensed. All right?
Yeah, I'm just saying that, like, do you need to, like, I see that there's the 2p like written 3 times, but do you need to have like the subscript of X, Y, and Z written on the subscript?
Yes, you do. Yes, you do.
Okay, thank you.
Now, so expanded in expanded electronic configurations, s orbital is never split. It stays as it is. You saw the diagram. P orbital can split px, py, and pz in a 3 different coordinates, 3-dimensional. S orbital can split 5 times in the 5 different dimensions or 5 coordinates. I gave you, right? dx square minus y square, dy square minus dz square, dxy, dyx, dzx. You remember 5 of them. F orbital can split 7 times, 7 coordinates, and each coordinates have 2 electrons. So 7 times 2, 14 electrons, right? S can hold 2, P can hold 6, D can hold 10, F can hold 14, 1/4. G orbital can split 9 different orbitals. G orbital can split 9 different orbitals. 9 different orbitals. 9 different orbitals. And that 9 times 2, you'll have 18 total number of electrons. That's expanded electron configuration. We're not going to go too far from the F orbital, by the way. We'll start at D, but still you should know that. All right. So that's I showed you the shape of those orbitals, the period specifically. Now this is the electron distribution of those elements. Question? You have a question?
Yeah. What do you mean can split 5 different ways? Can you like review that?
I don't think so. No, you don't have to. You don't have to. You mean D can go to 5 different coordinates, 5 different dimensions, right?
The
Yes.
fuck did he
Like,
just
I'm not
say?
following.
Okay, tell me, what's the question?
When on the last slide it said can be split into 5 different ways. What do you mean by that?
Meaning 5 different coordinates. So for example, let's say P can split into 3, right?
Okay.
So these are 3 coordinates, Px, Py, and Pz in a 3-dimensional. So if you have a D, it will be 5 different like this kind of things. 5 different ways. If you have a F, it will be 7 different ways like this kind of distribution. If you have a G, 9 different distribution like this. Obviously, there will be too complex, right? We're not going to go that far. We're not going to go that far. Is it okay? All right. So let's go to this is the electron distribution at the outer shell of an element. So let's take a piece of paper, please. Take in your notebook. Do not write from top to bottom. Write from side by side, left side to right. Write down electronic configuration of the element. That's the element right here. Those are all the elements. Condensed, expanded, number of electrons in the outer shell. Do the heading because there will be many of them. At least we'll go 20 of them. Okay, maybe 30. Whatever. We'll make a cut short. So number of electrons in the outer shell, position of the periodic table, and LDS. The last column is the LDS. LDS stands for Lewis dot structure. Lewis dot structure. And we'll see it. I did not put it there, but I will once the time comes. Structure. STRUCTU. All right. TU. Oh, there is no space there. RE. So let me spell it all together. So Lewis, LEWIS, Lewis for L, dot for D, structure, 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 Lewis dot structure. Now, do you have those columns? Tell me when you have those columns. So electronic configuration of an element, that's the name of the element, and the top one says the atomic number, right? That's atomic number. Atomic number is number of protons that equals to number of electrons. Condensed, expanded, number of electrons in the outer shell, position of the periodic table, and finally how to write the Lewis dot structure of an element. That's basically it is. How to represent in terms of Lewis dot. Lewis is the name of the scientist, by the way. Okay. Element number 1, first element, atomic number 1, it has 1 proton in the nucleus, 1 electron in the outer shell. Therefore, it will go to the first shell or subcell or whatever you want to say. S doesn't split. So it's 1s1, 1s1. So the electronic configuration of hydrogen is 1s1. It has only 1 electrons in the first cell, S1s. Number of electrons in the outer shell, 1, of course. Position in the periodic table, 1a. So group 1a. And Lewis dot structure is the number of electrons in the outer shell. That's basically represent. So you just put a dot. That's all. 1 dot, that means 1 electron. So the hydrogen represents the nucleus of hydrogen, and 1 dot represents the number of electrons in the outer shell. So that's the number 1. That's the 1 electrons. That's a dot. Now, who can tell me, do you think hydrogen as it is, H dot H, do you think is hydrogen stable? If you have an element that's 1 electron in the outer shell, do you think it's stable? Yes? Stable means can it stay as it is? Because remember the spin period. Say it again?
No.
No, because it needs to be spin paired. That is absolutely right. So if you need to have spin paired, then how will you do it? So what hydrogen does, it takes another hydrogen atom next to each other, make another dot, and make a bond. That's a 1 electron spinning counterclockwise, another clockwise. The 2 hydrogen can stay together. So hydrogen always exists as H2. It doesn't exist like H because H is not stable. So hydrogen always exists as H2. It is also known as, you're writing, it is also known as diatomic, atomic element. Diatomic element. Hydrogen is one of the 7 diatomic element. I just give you one. I also explained to you why it is makes H2, because the Lewis dot structure has only 1 electron in the outer shell, 1 dot. 1 electron is not stable because it's spinning in one direction, creating North Pole and South Pole. It is not stable. Once you have another electron of the same kind from the hydrogen, for example, now that they are spinning in opposite directions, they're spin paired. Now they can make a bond. Who can tell me what's the bond name of this bond? Does anyone know what's the name of this bond? H bond H. Anyone? Do you know the name of the bond?
Hydrogen bond.
No. Very good point though. Very good guess though. It is a covalent bond. Covalent. It is called covalent bond. Covalent bond. Covalent bond is the sharing of pair of electron. Sharing a pair of electron called covalent. C-O-V-A-L-E-N-T. Covalent bond. Covalent bond. But it's a good guess though.
I have a question.
Say it again.
I have a question.
Yeah.
For the Lewis dot structure, do we write like just the dot, or do we have to write the bond if it's?
No, dot. Just a dot. But I showed you that hydrogen doesn't exist as a H because of the instability, as you said, and therefore we want to the covalent bond. Is okay? All right. Let's go to the helium. So the helium is as 2 atomic number 2. 2 protons are in the nucleus along with the neutrons, and 2 electrons in the extranuclear space. And therefore 1s2 is filled up. 1s2. S can hold up to 2 electrons. 1s2. So position in the periodic table is the number of electrons in the outer shell is 2, right? But position in the periodic table is 8a. Who can tell me why it is 8a? Who can tell me why it is 8a?
Because it's a noble gas.
Yeah, thank you. Because yes, helium belongs to the family of noble gases, noble gas elements. That is correct. Or inert gas element, they do not react. The outer shell is completely filled up, and all those other noble gas elements, they also have 8 electrons in the outer shell. Also, we'll get it very soon. That's why it is present in the group 8A. Very good point. Now, the Lewis dot structure will be 2 dot, right? 1 dot, another dot. That's it. And 2 dots, so they are pretty stable, spin pair. Therefore, they don't have to worry about, they don't make any compound. They're inert gas. Now, atomic number 3, 3 protons in the nucleus holding the 3 electrons in the extra nuclear space. Therefore, the electron distribution, first shell is filled up, outer shell is 2s now. Remember
Maybe
that
I'm not
diagram
recording
I
it.
showed you, those the cross section of the atomic structure. So now 1 is filled up, it goes to second highest energy level is a 2s1 because it has only 3 electrons. S can hold 2, but it has only 3 electrons. So number of electrons in the outer shell is 2s1, 1 electron. Therefore, it is 1 electron in the outer shell. It belongs to group 1A. And therefore, lithium, the electron dot configuration of lithium is just 1 dot. Lithium dot. That's it, right? Beryllium, Be, atomic number 4, 4 protons in the nucleus, 4 electrons in the extranuclear space. The electronic distribution, 1s2, 1s2, first shell is filled up, second shell has 2s and 2p, only 2s is filled up, 2p is still there, empty, but it doesn't have enough electrons, so it has 2s2, and the number of electrons in the outer shell is 2, it is group 2A, and the Lewis dot structure will be, you can put just like this, 1 electrons there, 1 electron there. It doesn't matter how you put it, but at least if you put the 2 dots, meaning that's a Lewis dot structure. It has 2 electrons in the outer shell. So if you know the elements in the periodic table, you can also know the dots, basically, in fact. They correspond perfectly fine, 1 to 1. And also the number of electrons in the outer shell, group number, and the dot number. Exactly, they're all 1 to 1. Boron, atomic number 5. So 5 electrons in the outer shell, 5 protons inside the nucleus. They're holding those 5 electrons, and those electrons are distributed 1s2, 2s2, and 2p2. So the outermost shell is 2s, is a 2. That's the number, that's the outermost shell, and it is S and P. S is filled up 2, and P has only 1. P has only 1 because you have only 1 electrons. Now this is the condensed. This is the condensed electronic configuration. So wait a minute, just a minute. Come on. All right. So this condensing, this one you can expand it. So that come on, what is going on here? My cursor. Don't worry about it. I'm coming. Okay. All right. So the 2s2 and 2p1. So the expanded electronic configuration will be 1s2, 2s2, and then you have to write 2px, right? 2px, 2py. You don't have to write 2py, but I'm just showing you again. 2pz, 2pz. You have a px, py, pz, this p, but you have only 1 electron. It will go to 2px1. These are all 0, 0. You don't have to show it. If you show it, doesn't matter. Show it perfectly fine. If you don't show it, still is okay. Because it has only 1 electron, it goes to 2px1. Why you can say that, why not 2py1 and 2px0? Yeah, you can say it, but x, y, z are a common thing, right? That's basically we know. And that's basically, so it goes to 2px1. Number of electrons, outer shell, 2 plus 1, 3, and therefore 3. Number of electrons, outer shell, 3.
That's hilarious.
Group 3A, and it has a 3 dots. I'm going to write like this way. So it's a 3 dots, meaning 3 electrons in the outer shell. Boron. Go to carbon. Carbon has a 6 atomic number 6. 6 protons in the nucleus, holding 6 electrons in the extranuclear space. Therefore, distribution is 1s2 in a cell, 2s2 and 2p2. That's the second cell. Filling up 2 cell is complete. 2p is filling up progressively. So, come on, okay. 2p is filling up. And therefore, so what you have, this 2p, so the expanded one will be, you write the same thing, 1s2, 2s2, then write down 2px, 2py, 2py and 2pz. All right, I'm just writing it because they are x, y, z, right? Now you have 2 electrons. Tell me, how did it go fast? You'll go to 2px1, 2py1, and 2p0. You don't have to write the 2pz then, because it's 0. So this distribution is 1, 1. You cannot write 2px2 and this is 0. As I told you, Hund's rule, they will have an equal share first. It will go, electrons will go one at a time to all those available same energy orbitals. Px, Py, Pz are the same energy orbitals of P subcell. So therefore 1, 1. That's a distribution, the expanded configuration. Number of electrons in the outer shell is 2 plus 2, 4, and that's a 4. All right, and it's group 4a, and therefore you have this, that, and that. 4 dots. Carbon surrounds 4 dots surrounding the carbon nucleus, and therefore 4 electrons in the outer shell. Number of electrons in the outer shell 4, group 4a, and 4 dots. Atomic number 7, nitrogen. 7 protons in the nucleus, 7 electrons are distributed on the extranuclear space. 1s2 is filled up first, 2s2 filled up second, and 2p3, because you have 3 electrons, right? 3 additional electrons, and therefore the expanded will be same thing, 1s2, 2s2, they don't split, 2px, you write 2px, 2py, and 2pz, all right, 2pz. And you have 3 electrons, they have the same energy layers, according to Hund's rule, 1, 1, and 1, 1, 1 each. So equal distribution. And that's basically the Hund's rule. When you have a multiple same energy orbitals, electrons will be distributed 1, 1, 1 first. Then if you have additional electrons, which are like oxygen, then they will pair up. So nitrogen has like this. Now, in the outer shell orbital of nitrogen, you have a 2s2 and 2p3. 2p3 distributed like this, 2s remains as it is. So it belongs to group 5a, 5 electrons. And now you write the Lewis dot structure. Please pay attention, very important here. These 2 electrons that I'm writing 2 dots right on the top, that belongs to 2s2 because it's spin paired. Other 3 are not, 1, 2, and 3. And these 3 are 2px1, 2p1, 2pz1. These 2 electrons that you have, 5 electrons, nitrogen has 5 electrons. These 2 electrons have never been used to make bonds. These 2 electrons never been used to make a bonds. Why? Because they're already spin paired. They're pretty stable. These 3 are the one who will make a bond with some other element, So these 2 electrons, that I have put the cursor a little bit closer. These 2 electrons called lone pair. Lone, L-O-N-E. Write down lone pair. Lone pair is also known as PAIR, okay? Lone pair of electrons. So lone pair of electrons, it is also known as unbonded pair of electrons. So those 2 pair electrons never been bonded with any other elements. Lone pair electrons. And why it is so? Because 2s2 is pretty stable. They're already paired up with the spin pair. Now these 3 electrons are unpaired. So therefore they can make a compound. So let's say if they want to make a compound with the hydrogen has 1, right? Remember, hydrogen has 1 electrons, 1 dot. So nitrogen can use that dot from hydrogen. Another hydrogen can also use from another dot, and another hydrogen can use another dot, and now basically you can make a bond. This is bond. So by these unpaired electrons, now they can bond, right? So the compound with N and H is NH3. What's the name of the NH3? Anyone knows the NH3? Is ammonia, NH3. So nitrogen has 5 electrons in the outer shell. two of them are never been bonded with anything else. They're called unbonded pair of electrons, or lone, L-O-N-E, pair of electrons. Three unpaired electrons, px1, pi1, pz1. Those three can bond with some other elements. For example, which element has one electrons, unpaired electrons? So hydrogen has one unpaired electrons. It can make the bonding with the hydrogen. Therefore, make the NH3, that's ammonia, NH3, ammonia. And these are covalent bonds. They are covalent bonds. Any questions? Any questions at this moment? So if not, go ahead.
So we're like oxygen, so you can't do the experiment.
I'm coming to oxygen. I'm coming to oxygen now. So oxygen has 8 electrons outer shell. Distribution is 1s2, 2s2, and 2p4. So the expanded one, 1s2, 2s2, and then 2p, 2px, 2py, 2py, and 2pz, 2pz. And that's the expanded one, right? 2pz, 2pz. So you have 4 electrons, they'll go 1, 1, 1 first. Then you have a 1 plus 1, so 1, 1, and 1. Right? Just like nitrogen. You have additional electrons, one more. So now it will have 1 plus 1. So 2px will have a 2. 2px will have a 2 electrons. And 2py and 2pz have a 1, 1 each. It has a 6 electrons in the outer shell. It belongs to a number of electrons in the periodic table. Position in the periodic table is 6a, 6a. And you'll be writing the oxygen. I'm writing it oxygen right here. It's better to see a little bit better because I don't have this hydrogen is blocking it. So oxygen, let's write it here, oxygen, O. And it is a 2 pairs, 1, 2. And those are the 1, 2s2. Then 2px2, also another pair. They're stable because they are basically with a spin pair, they're stabilizing themselves. And these two, they basically are unpaired. That's a 2px, a 2py1, 2pz1. So now, these two, this is one pair, unbonded pair of electrons. This is unbonded pair of electrons, and these are called lone pairs. The two of them, oxygen has 2 lone pairs. 2 lone pairs. Or unbonded pair of electrons, 2 lone pair of electrons, 2 pairs, 2 lone pairs. All right? They are called lone pairs of electrons. And oxygen has 2, nitrogen has 1. Oxygen has 2 unpaired electrons, 1 there, 1 there, 2py1, 2pz1. So if it wants to make a bond with other element, for example, hydrogen, H, it can make it. Hydrogen has 1 electrons, it can make a 1 bond, a covalent bond. Likewise, if you take 1 H, that has also 1 electrons, and it can make a bond. Tell me what is that molecule? Yes, tell me.
The time is now 11:50.
Oh, really? All right. Okay, thank you.
He was so
It's a very
sad.
short time, huh? That's all right. We'll continue. We'll continue for Friday. All right, thank you for letting me know. I still need to watch here. All right, very good. All right, that's fine. Thank you very much. We'll see you Friday.
Thank you.
If you have a question, I'm still here.
Have a good day.
You're welcome.
Thank
You too.
Oh, I guess I should.